Hi guys. So I'm going to go ahead and do a video on this one too. That's going to be a little bit better than the one during class. So this will help everybody who was struggling a bit with some of the math stuff. Okay, so mechanical energy and work. The equations we're going to use are here. You have your kinetic energy equation. You have your gravitational potential energy equation. We're going to use G equals 10 meters per second squared. Work equals force times the distance. Work also equals changes in energy. Mechanical energy is equal to Ke plus Pe. In the case where mechanical energy is conserved in a system, mechanical energy initial is going to equal mechanical energy final. If we expand that out, because mechanical energy equals Ke plus Pe, we get that initial, kinetic energy initial, plus potential energy initial equals kinetic energy final plus potential energy final. Lastly, kinetic energy initial plus potential energy initial plus work equals kinetic energy final plus potential energy final. This is the case where work is done on a system. All right, so let's get started. All right, let me move myself over. Why can't? Oops, nope, I don't want to be big. There we go. Okay. So, all right, when there are no outside forces or work done on a system, mechanical energy is conserved, and we have been practicing this. Okay, so here at the bottom, you have 100 joules of kinetic energy. It's all kinetic energy. Um, when you reach the top, the kinetic energy has all converted to potential energy. It's 100 joules. And then when you're a little bit more than halfway down, you have a lot of this potential energy has now converted into kinetic energy as you gain velocity and lost height. And so you have a little bit more kinetic energy than potential energy because we're a little bit more than halfway down. If we were to figure out the mechanical energy at any point in this motion, it would be the same because it's conserved. So at the bottom, the Ke plus the Pe is 100 plus 0, which is 100 joules. At the top, 0 kinetic, but 100 potential, 100 joules. And partially of the way down, it's 60 plus 40 is 100 joules. So it is conserved. So the mechanical energy of the system is 100 joules at any point in the system since it's conserved. So again, if there's no work done in the system, the mechanical energy of the system won't change. So we can use that mechanical energy to then find kinetic energy, potential energy, we can find velocities, we can find heights, because we can use this idea that the energy, the total energy of the system in mechanical energy of that system is not going to change. So in this case, let's look at this little example here, which is a good example to show it. Okay, so here's our equation. Mechanical energy initial equals mechanical energy final. And if we expand that, we end up with kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final. And we've been working with gravitational potential energy as our type of potential energy. So I can pick any point in this system, and the amount of energy, the amount of mechanical energy, should be conserved. So the Ke of this point should equal the Ke plus the Pe of this point down here. And it is true. So 20,000 plus 30,000, which is the Ke and the Pe, equals 50,000 plus 0. 50,000 plus 0 is 50,000. So 50,000 plus 50,000, mechanical energy initial equals mechanical energy final. The mechanical energy of the system is 50,000. So at any point, this person has 50,000 joules of mechanical energy, which is either all potential at some points, all kinetic at some points, or a mixture of the two. It's all potential when that person is at the top, and it's all kinetic when that person is at the bottom. Anywhere else, it's some mixture of the two. So let's look at this example, which in class, I think some of you were like, okay. A 5 kilogram rock is traveling at 15 meters per second in the upward direction. Okay, let's stop right there. I have a mass, 5 kilogram. I have a velocity, 15 meters per second. That's enough for me to figure out kinetic energy. It leaves a person's hand and it's 1.5 meters above the ground. So I'm taking a rock, I'm throwing it up, and it's already 1.5 meters above the ground. So it's a 5 kilogram rock traveling 15 meters per second as it leaves the hand, which is already 1.5 meters above the ground. So the question I'm asking is, how far above the ground will it be when it's going 5 meters per second? Okay, let's not panic. We're using KE initial plus PE initial equals KE final plus PE final. And I know that when I'm looking for a height, that is going to be filed under gravitational potential energy because that's mass times gravity times height. So, okay, here's how this is going to look. KE initial plus GPE initial. I can find those because I have that information in my problem. I have a mass, 5 kilograms. I have an initial velocity, 15 meters per second. Okay. I also have, for potential energy, I have the mass. G is 10 meters per second squared, and height is 1.5 meters above the ground. I also have my KE final. Okay. That is going to be, I have a velocity squared, 5 meters per second. So basically what I'm saying is that the energy I have initially has to be the same total amount of energy I have when this rock is 5 meters per second at some point above the ground. So when we plug the numbers in, we end up getting 1/2 times 5 times 15 squared, which is my initial kinetic energy, plus mass times gravity, the acceleration due to gravity, times height, so 5 kilograms, times g, which is 10 meters per second squared, times height, which is 1.5 meters, which is in the problem, is going to equal my final kinetic energy plus my gravitational potential energy. So my final kinetic energy is 1/2 times 5 squared plus the GPE. So I end up getting 562.5 joules of initial kinetic plus 75 joules of initial potential, gravitational potential. So together, my energy amount here are these two added together. That is the mechanical energy of my system. It cannot change. Okay. Now, when the rock is going 5 meters per second, the kinetic energy is 62.5 joules, and the rest of that mechanical energy is going to be GPE. So if I want to find my gravitational potential energy, oops, sorry. So gravitational potential energy is going to be 562.5 joules plus 75 joules. That's going to give me the initial mechanical energy. And then if I subtract 62.5 joules, it will give me my portion at the end, which is gravitational potential energy. So it's 575 joules. Now, we can find the height by using that 575 joules of gravitational potential energy, which is what the potential energy is when that rock is traveling 5 meters per second squared. And I can use that to find the height. So 575 joules of GPE is equal to mgh. And I have a mass, which is 5. I have a 10 meters per second, which is g. And my height is what I'm looking for. So 5 times 10 is 50. So if I take and divide 50 by both sides divided by 50, algebra, 575 divided by 50 is going to give me 11.25 meters. So when that rock is traveling 5 meters per second, the height of it is 11.25 meters. Whew. Okay. So let's try another one. So you have a 45 kilogram skateboarder, and they're traveling at 4 meters per second as they reach the bottom of a ramp. So the lowest point of the ramp. So all of the mechanical energy is kinetic energy. There's no gravitational potential energy. It's all kinetic energy at this point because they're at the fastest point that they're going to be going. Their velocity is the greatest. So I want to know how high the ramp is. Okay, so, and I give you a little hint. We'll come back to the hint. The answer, first of all, KE plus GPE equals KE plus GPE. I took off the initial and the final for some reasons. One, I don't want you to think that it has to be the initial and the final. It's basically at any time during motion where energy is conserved, where mechanical energy is conserved, the kinetic energy and potential energy of one point is going to equal the kinetic energy and potential energy of the other point. So I took away initial and final just so that you realize it doesn't have to be the ultimate initial and the ultimate final. So 1 half mv squared plus mgh equals 1 half mv squared plus gpe. And gpe here, this final, is what's going to give me my height. Now, this is a pretty simple equation compared to the other one because at the get-go, I have 45 kilograms and I have a speed, I have a velocity, 4 meters per second, but I'm at the bottom of the ramp, which means I have no height. So initially, nothing is gravitational potential energy. All of the mechanical energy is contributed to with the kinetic energy. Then I want to know at the end how high the ramp is. Well, the velocity when I'm at the top of the ramp is going to be 0. So on the other side of the equation, my kinetic energy is going to be 0 because there's no velocity. And so I'll be able to find all three of those variables: initial kinetic energy, initial gravitational potential energy, final kinetic energy, and then I'll just be able to calculate my gravitational potential energy and then use it to find my height. So we plug it in. 1 half times 45 times 4 squared, which is the velocity, plus mgh for my GPE. Mass is 5, g is 10, 0 is height. Guess what? Anything multiplied by 0 is 0. Equals 1 half, 5 is my, oops, sorry, I should have 45 there. Oops, sorry guys, that should be 45. My bad. Must change. 1 half, 45. But it doesn't matter because the velocity is 0. So it's 0, so it's 0. So that is a mistake on my part. Plus GPE. So in this case, 360 plus 0 equals 0 plus my GPE. So guess what? It's all kinetic energy in this problem at the beginning, and it's all gravitational potential energy in this problem at the end. So GPE is 360. So the GPE at the top is 360 joules, and now I can use that to find my height of the ramp, assuming that the skateboarder is at the top of the ramp. So GPE at the top is 360 joules. So 360 joules is mass times gravity times height. Mass is 45, gravity is 10, height is what I want to find. So 45 times 10 is 450. Divide both sides by 450 to get a height by itself as an isolated variable, and I get height equals 0.8 meters. So that's how high my ramp is. Not the highest height. It's a little bit less, a little bit less than 3 feet. Okay. All right. So that is using the conservation of mechanical energy. But one final thing to say. When mechanical energy is conserved and there's no friction, then the path taken for individuals has no effect on the change from KE to GPE. So they don't lose any energy on the way. So what does this mean? Well, let me just walk through this. Okay. Two people each have 2,000 joules of potential energy at the top of what we call a frictionless slide. So there's no outside forces. Person B slides down the slide, whoop, while person A jumps off the back. Obviously, person A, you think they're going to be going faster, right? Well, no, they're going to be going the same speed because 2,000 joules of potential energy was all converted to 2,000 joules of kinetic energy. Kinetic energy is 1 half mv squared. Each individual is going to be going at the same speed. No. All right. So let's talk about what happens when there's work. Oh no, I've added work. Okay. So what about when there are outside forces that cause movement? Okay, then work has been done on the system and that changes the energy of the system. So work, aside being a force times a distance, okay, it is the change of energy in a system. So the work energy theorem is that work equals the change in the total energy of a system. So if you do work on a system, either in the form of kinetic energy or in the form of potential, like adding potential energy, like gravitational potential energy, you have done work on the system. So now one thing we can do about this equation to make it a little bit easier, let me just go back to the equation. So this looks confusing, but all we've done is we've just said we're going to add in the amount of work that was done. So usually work changes the kinetic energy, so we can often simplify the equation a little bit. Okay. So instead of having KE initial plus PE initial plus work equals KE final plus PE final, for our level of class, usually we're either just adding work to the kinetic energy side or just adding work to the potential energy side of it. So you can say, like, for example, kinetic energy initial plus work equals kinetic energy final, because if potential energy is not changing at all, the object is not moving up and down vertically, okay? Well, for gravitational potential energy, because there's other types, but we can go ahead and just ignore that type of energy and just focus on the one the work is done on. Okay. So, last thing before we do some practice problems, positive and negative work. Positive work causes the energy of a system to increase. So I said at the beginning, work is not a vector quantity. Okay. What allows work to be positive or negative just has to do with whether energy is inputted into the system or if energy is taken out of the system or removed from the system. So positive work causes the energy of a system to increase, where the outside forces acting in the direction of motion do positive work. So if the force is in the direction of motion, work is positive. It increases the energy of the system. Negative work is the opposite. It causes the energy of the system to decrease. So the outside forces are acting opposite the direction of motion, and that's negative work. So here's a little table. Move myself down. Okay. So if a force is in the direction of motion, that's positive work. If it opposes motion, that's negative work. Now, if a force is 90 degrees to motion, there's no work done in the direction that was 90 degrees. So for example, if you're talking about having horizontal motion and work is done in like the vertical, there's actually no work done in the horizontal motion side. So we don't consider that any work done because work was only done in the vertical, not the horizontal. Don't worry so much about that. And then if the object's not in motion at all, there's no work. Okay. And the reason we can say that that 90-degree thing is because there's no force done that has any part of it in the direction motion was at all. Okay, so example one. A 4 kilogram box having 200 joules of kinetic energy initially slides across the floor before being pushed forward with a velocity of 2 meters per second. Okay, so let's figure this out. Okay, what is the work done on the box? Okay, here's where you have to consider you can have two choices here. Either the problem gives you the force and a distance, and you can use work equals force times distance to figure out the work, or you have to think it's a change in energy because the problem gives you either a velocity or a height change, and you're going to have to calculate what was added to either kinetic energy or either added to potential energy. In this case, we can, well, this kind of explains that. So work is equal to change in kinetic energy. So you could use work equals force times distance, which is nice if the problem gives you the force and the displacement. Or I have to think of it as like, oh, work equals change in kinetic energy in this case. So it's 1/2 mv squared because I have a velocity. So I'm going to use work equals 1/2 mv squared because I have a mass and I have a velocity. So the work, what was added energy to the system, is 1/2 the mass of 4 times the velocity of 2 meters per second squared. So that is 8 joules. So 8 joules of energy was added to this box that was sliding across the floor. That was the work that was done on it. Now, what's the final kinetic energy of the box? Okay, so kinetic energy initial plus work equals kinetic energy final. So I actually know my kinetic energy initial. I know the work, so I can easily find the final kinetic energy. So 200 joules is the initial kinetic energy plus the work, which is 8. So the final kinetic energy this box has is 208 joules. Now, was the work positive or negative? Options. Did energy increase or decrease? Increase positive, decrease negative. Also, was the force in the direction of motion or was the force opposing motion and in the opposite direction of motion? Well, in this case, it was positive because the energy increased and the force was in the direction of motion. Either of those can tell me that it's positive. You don't need both to happen for it to be positive work. Okay, so example two. A 2 kilogram bowling ball has 1100 joules of kinetic energy as it rolls across the floor. It encounters 20 newtons of friction force for 30 meters. Okay, remember the direction friction force is. It is in the if it's moving this way, friction force opposes it. So what is the work done on the bowling ball? This one's really nice because I actually have a force and a distance. So change in KE or force times distance, and I get to use a force times a distance because I'm given force and displacement. I use distance and displacement interchangeably, sorry. So work is equal to 20 newtons times 30 meters, but since this is friction, which is opposing motion, the force is negative. So the work is negative 20 newtons times 30 meters. So the work is negative 600 joules. So be careful if I'm talking about friction or some form of work being done opposite the direction of motion. Now, so is the work negative or positive? Well, this one's a pretty easy one. We just showed you it was negative. It's negative because it is the friction force itself opposes motion. And in the end, I'm going to be removing energy from the system. And what it's going to be is it's going to turn into thermal energy because anytime there's friction involved, some of that energy converts to thermal energy. So probably the energy I'm taking from the system is going to convert into thermal energy that leaves the system. So, what is the final kinetic energy of the bowling ball? Well, this one's pretty simple. Kinetic energy initial plus work equals kinetic energy final. So, kinetic energy initial plus work equals kinetic energy final. My initial kinetic energy was 1100 plus a negative 600 equals 500 joules. Voila. All right, let's do one more tough one. Not tough, but it just requires you to do the most amount of calculations. All right, now we have a 3 kilogram box that's already sliding to the right at 4 meters per second when a person pushes it to the right again with 12 newtons of force for a distance of 1.5 meters. Okay, so now, does this person do positive or negative work on the box is the first question. How much energy does how much does the energy of the box change? So what's the change in energy, which is also equal to the work done? And then how fast does the box end up going? Let's see if we can figure this out. And to figure out how fast the box ends up going, you're going to use kinetic energy first because you have to find the initial kinetic energy. You're going to have to add that initial kinetic energy to the work to get the final kinetic energy, and then use the equation for velocity that from the kinetic energy equation to figure out the velocity. Okay. Now, so do they do positive and negative work? So did they add energy? We don't really know that yet. We haven't done the problem yet, but was the force in the direction of motion or not? Well, the box was sliding to the right, okay, and the person pushed it to the right. So yeah, it was in the direction of motion. So that tells me it's positive work. So yeehaw, we are increasing the energy in this system. Okay. Now, how much does the energy of the box change? Well, work equals a change in energy. And lovingly wonderful in this one, again, I have a force and a distance. So it's really easy to find the work done because the force is 12 newtons and the distance that person pushed it to the right is 1.5 meters. So work done is 18 joules. That's the easy part. Now comes the hard part. How do I know how fast the box is going at the end? Well, I have to know the final kinetic energy. In order to do that, I have to know the initial kinetic energy. I have to know the work. I've already calculated the work. And then I have to be able to solve for velocity. But no matter what, I have to know the final kinetic energy because that is how I'm going to get velocity. So we're going to use KE equals 1 half mv squared to find the initial kinetic energy. We're going to use KE initial plus work to give me the final kinetic energy. And then I'm going to use the equation for velocity that works with the kinetic energy equation. So, initial kinetic energy. I have a mass of 3 kilograms and I have a velocity of 4 meters per second. So, 1/2 times 3 times 4 squared. The initial kinetic energy of this box is 24 joules. Right? Well, now I just add that to the work, or the work to the initial. So kinetic energy initial plus work equals kinetic energy final. So 24 joules plus 18 joules of work gives me 42 joules, which is my final kinetic energy. Woohoo! Now, you can solve for velocity. It's not hard to do using 42 joules equals 1/2 mv squared because you know the mass and you know the final kinetic energy. But I've also provided you with the equations. So velocity, when you have the variables for kinetic energy, then velocity equals the square root of the product of, well, square root of 2 times your kinetic energy divided by your mass. So velocity equals square root of 2 times the final kinetic energy, which is 42, divided by the mass, which is 3 kilograms. Why 42? Because I want to know how fast the box ends up going. I already know how fast it was going initially. It was going 4 meters per second. I want to know how much faster it's going now. So how fast is it going at the end? So I'm using the final kinetic energy to figure that out. So 2 times 42, which is 42 joules was the final energy, divided by the mass, which is 3, and the square root of that whole thing, and I get the velocity equals 5.3 meters per second. Okay, so there you go, guys. That is how we're going to use these equations. All right, I'm going to stop.